will analyze a rigid frame which is shown in this figure. So let us start to solve this problem by matrix stiffness method using system approach, right? So very first is the decay value. So the decay value here is, it is 2, which is theta B and theta C. See, joint A is fixed, you don't have any deformation here. Joint B is the intermediate joint, which is you have a rotation at B here, right? And joint C, you have a rotation as it is hinged here, so you have rotation at C also. But the axial deformation here, this deformation, the axial deformation at B and C, right, which is sway, which is 0 here. Why it is 0? Because you have a reaction here, right? So this reaction will take care of this sway. So therefore it is a non-sway problem. Is it clear? So this problem is a non-sway problem, right? So you have only two deformation, which is theta B and theta C. Clear? So let me assign the coordinates number. I'll just give the numbering for this. Let this be coordinate number 1, let this be coordinate number 2. Clear? So now calculate the stiffness matrix. So what is stiffness matrix here? Stiffness matrix is stiffness matrix K. How to develop the stiffness matrix of the first column? So the stiffness matrix for the first column, we give first column, give unit displacement at coordinate 1, unit displacement at 1, and calculate forces at 1 and 2. Calculate forces at 1 and 2. So I'll just draw the figure for this. This is the figure frame, right? I have unit rotation. Where is coordinate number 1? Coordinate number 1 is at B, right? So the coordinate 1 is at B. So this is 1. So when joint B is I am giving unit rotation at joint B, then the members connected at joint B, that is BA and BC, will rotate in clockwise direction, right? So it will rotate in clockwise direction like this and this, right? So this deformation is 1. This deformation is 1. So when this deformation is 1, the force here is, the force at the applied where you have applied is 4EI by L here, and the same here it is 4EI by L. And at the other end, it is 2EI by L here. 2EI by L, half of it. You have force at A also, but I'm not interested at A. I have coordinate at only B and C. So it is 2 degree problem. So these are the forces. Now what is K11 now? K11 will be equals to, it is at A. This is A, this is B, this is C. The coordinate 1 is at B. So at B you have two forces, 4EI by L for BC member and 4EI by L for AB member. So 4EI by L for AB member plus 4EI by L for BC member, right? Substitute for EI and L for this. I is different. For AB it is I, and for BC it is 2I. Clear? So 4E into I for member AB is I. Length for member AB is 5 plus 4E into I for BC member is 2I, and length is 4. So if you calculate this, it will be 2.8 EI. This is K11, right? What is K11? K11 is force at 1 when the unit deformation is at 1. The force at 1 when the unit deformation is at 1. So similarly, K21, force at 2 when the unit deformation is at 1. So what is that? The coordinate number 2 is at C. So at C, the force is 2 EI by L, and both are clockwise direction. So it is plus 2 EI by L. But this is for which member? This is for member BC, right? This is for member BC. Substitute the values for this. You have 2 EI for BC is 2I, and length for BC is 4. So it will be EI. It will be EI. This is the first column. Next column, second column. How to develop the second column? Give unit deformation, unit displacement at 2, and find forces at 1 and 2. How do you determine this? I'll draw the figure for this. This is the frame, right? I am giving unit deformation. The force which I have applied, which I have given the coordinate number 2 is clockwise. It is at C, right? So when you are applying a couple at C, the member connected at C is CB. So it will try to rotate in clockwise direction. So it will hog up, right? This is unit deformation, right? Where you have applied, it will be 4 EI by L, and the other end with the same direction, it will be 2 EI by L. But the member AB will not rotate. Clear? Only member BC will rotate. Now equate this, you will get K12, the force at 1 due to unit deformation at 2. Where is 1? 1 is coordinate at B. So at B, you have 2 EI by L. So it is 2 EI by L. So this 2 EI by L is for member BC, right? And substitute. So it is 2E into I is 2I divided by 4. If you calculate, it will be EI, and this is equals to K21. Here, similarly K22. K22 is deformation at 2 due to unit displacement at 2, right? So where is 2? 2 is at C. So at C you have 4 EI by L. So this 4 EI by L is for BC member. So if you substitute for BC member, 4E into 2I by L, 4E into 2I by L is 4. So it will be 2I. Right? This is the 2 by 2 matrix. So therefore your K matrix is, first column is 2.8112 into EI. So this is simple, your K matrix. Clear? After getting K matrix, your third step is locking forces. So what are the locking forces? Locking forces are, it is P dash. So calculate the forces. You have, what are the forces here? You have the loading at BC as 40 kilonewton, which is at central point load, and for AB you have eccentric point load, which is 50 kilonewton. Clear? So you have to calculate the fixed end moments here. So this fixed end moments are, this is member BC, this is member AB, right? I will show the load here. It is 50 kilonewton load here, 50 kilonewton load. Distance is 2 meter and 3 meter. And here it is central point load, which is 40 kilonewton load, which is 2 meter and 2 meter, right? How do you show the uh, fixed end moments now? The fixed end moments will be, see, you have the load is along along this x direction. So this is, you can rotate the beam, right, with vertical loading downward. If you rotate that, this is anti-clockwise and this is clockwise, right? Suppose if the load is towards opposite direction, this direction, then you can rotate similarly, so that the load is vertically downward. The left will be the anti-clockwise, right will be the clockwise. So now this is the direction, and for this is anti-clockwise and this is clockwise, right? Now calculate the values. So these values, this is A, this is B, this is C. So how do we calculate this? MFAB, MFBA. MFAB, so this is eccentric point load. AB, MFAB is minus WA square B by L square minus WAB square by L square. A is 2 meter, B is 3 meter. If you substitute that, you will get minus 36 kilonewton meter. MFAB, MFBA will be plus WA square B by L square. If you substitute, you will get 24 kilonewton meter. And BC, it is central point load. MF BC is equal to WL by 8 minus WL by 8. So it will be minus 20. And MFCB will be plus WL by 8. It will be plus 20. So that means this is 36. This is 24. And this is 20 and 20. I have not shown minus plus sign because I have shown the directions. So these are the fixed end moments. Now calculate the locking forces. The locking forces at, where is 1? 1 is at B, it is clockwise. Coordinate 1 is at B here, it is clockwise. This is coordinate number 1. So along coordinate number 1, 20 is, sorry, I have shown it negative. This is clockwise, right? At 1, clockwise is at B. So at B, 24 is clockwise, 20 is anti-clockwise. So at B, the locking forces will be P dash, matrix P dash is equal to, at B, you have plus 24 and plus 24 and anti-clockwise 20 minus 20. So minus 20. And at C, coordinate C, so coordinate number 2 is here, which is clockwise, right? So at C, along coordinate number 2, there is only one force, which is 20, and it is in the same direction clockwise. So plus 20. Plus 20. So that means your P dash matrix will be 4 and 20. This is a P dash matrix. External forces, there is no external force here. Along coordinate number 1 and along coordinate number 2, there is no external force. 4 kilonewton meter, 2 kilonewton meter, there is no couple, external couple. You have only external force like 40 kilonewton and 50 kilonewton. So there is no external force. So external force matrix is 0. So P external force matrix P is 0, right? Now you have all the matrices. Now calculate the unknown matrix, unknown displacement. So what is that unknown displacement? This is 4th step. Now 5th step. Unknown displacement. How to calculate this unknown displacement? Delta is equal to K inverse into P minus P dash. Now you have the matrix as P is 0. This is 0. This is 0. So therefore delta will be equal to K inverse in minus of K inverse into P dash. Minus of K inverse into P dash. So it is minus, this is minus, and K inverse, what is K? 2.8. K is 2.8112. Inverse of this matrix with minus sign, and into P dash 4 and 20. This is 4 and this is 20. This is simple problem, right? And you have EI value, so that EI will be 1 by EI. That EI will be 1 upon EI, inverse of that. So 1 upon EI. So this will be minus 1 by EI into, how to do the inverse of 2 by 2 matrix? Interchange the principal diagonal elements. This is 2, this is 2.8, and change the sign of other two elements. So this is minus 1, this is minus 1, right? This is the cofactor divided by the determinant, 2.8 into 2 minus 1 into 1. That into 4 and 20, right? And if you simplify this, you will get it as plus 2.6 and minus 11.3, right? And 1 by EI is here, so 1 upon EI. So this is delta 1, this is delta 2. So what is delta 1? So delta 1 is corresponding to theta B, delta 2 is corresponding to theta C. Where is 1? Coordinate number 1 is at B, which is corresponding to theta B. Coordinate number 2 is corresponding to theta C, right? So you get it as EI, you take this EI to this side, so EI delta 1 is equal to EI theta B, which is equal to 2.6, and EI delta 2 is equal to EI theta C, which is minus 11.3. So this is clockwise rotation, this is minus is anti-clockwise rotation, right? So these are the unknown values. With these unknown values, what you need to do is you have to calculate final moments. So sixth step is final moments. How do you do this final moments? Calculate this final moments by applying the slope deflection equation. So what is that? MAB is equal to MFAB. MFAB is, what is MFAB? Which you have calculated. MFAB is minus 36. MFAB plus 2E. Shall I write the formula? Shall I just write the formula? MFAB plus 2EI over L into bracket 2 theta A plus theta B minus 3 delta over L, right? So what is this? MFAB is minus 36. MFAB is minus 36 plus 2EI for member AB is I only, divided by length of member. This is, what is the length of member AB? It is 5 meters. 5 meter. Take this EI inside. Take this EI inside into bracket 2 EI theta A. 2 EI theta A. Theta A is 0, right? There is no deformation there. EI theta B is plus 2.6 and delta is 0, right? Because it is non-sway problem. So delta corresponds to sway. So it is non-sway problem. So this will be equals to, so while applying this, you can take theta A, applying final moments, you take theta A is equal to 0 because it is fixed end, and you can take delta is equal to 0, it is, as this is non-sway. problem, right? And if you calculate this, this value will be minus 34.96 kilonewton meter. Similarly, you can do MAB, MBA. MBA is MFBA, which is 24 plus 2 by 5 into 2 theta B plus theta A. 2 theta B is 2 into 2.6, and the rest is theta A is 0, delta is 0, right? And this will be 26 kilonewton meter. BC, MBC is equal to MFBC minus 20 plus 2 by L, length for member BC is 4, into bracket 2 EI theta B plus theta C. 2 EI theta B is 2 into 2.6 plus theta C, that is minus 11.3. And if you calculate this, this will be plus 20 minus 26 kilonewton meter. So you may get some decimal point, but MBA should be equal to MBC. MBA and MBC should be same. And lastly, MCB. MCB is MFCB. What is MFCB? MFCB is plus 20 plus 2 EI over L, 2 by L, that is 2 by 4 into 2I. You have to substitute here. Here it is 2I. I have not substituted. This is 2. Please remember, you have to substitute 2I, right, for BC. So substitute 2I here. So this is into 2. You will get it into 2 here, right? Now here also into 2, that is 2I. Then bracket 2 theta C, 2 into theta C minus 11.3 plus theta B is 2.6, right? Minus 3 delta over L, 0. And if you calculate this, you will get it 0, right? You may get 0.001 or 10 to the power of minus 3, right? But that is 0. So that error you will get it due to decimal points. So why it is 0? So this will be a confirmation whether you have solved the problem correctly or wrong. It has to be 0 because you have the C joint is the hinged joint where the moment has to be 0. The bending moment has to be 0 there. So this is the final moments of the complete entire frame. You can draw the bending moment diagram for this if you want. It should be like this. I'll give you the line diagram for this. This is free bending moment diagram. You have point load here, right? So it is W L by 4. This is eccentric point load. So W A B by L, right? You can draw write that, and you will have movement here. What is the movement at A? The movement at A is AB. It is minus 34. Minus 34.96 is minus means, see how you should draw the bending moment diagram. So minus means it is anti-clockwise. It is anti-clockwise, right? Anti-clockwise. This is anti-clockwise. If I rotate this anti-clockwise for member AB here, this is A, this is B, then this member will deflect upward. So that means you have to draw ordinate upward. How much is this ordinate? This is 34 point something 9, right? And for BC, how much is BC? BC is AB. Next is BA. BA is plus 26. BA is plus 26. So plus means you just take member BA, don't take member BC, take only member BA. Plus 26 means it is clockwise, right? If I rotate this clockwise, the member BA will deflect upward. So that means you have ordinate upward. Clear? So this is the bending moment diagram. Clear? How much is this? This value is 26. So this is 26. Similarly, the BC value is minus 26. Minus means anti-clockwise. So if I have anti-clockwise couple for BC, so this beam BC will deflect upward. So it is plus minus 20. That is 26 only. So this is 26, and here it is 0. Join this. So this is your final bending moment diagram. This is the hatched portion, is the final bending moment diagram. This is how we can draw the bending moment diagram. Clear? What you need to do is take only the member which you want to draw it. Take member AB only, separately take the member AB, and get the moment value, whether it is clockwise or anti-clockwise. See whether the member with that couple, see whether the member deflects upward, downward, or left, right, and accordingly you draw the ordinate either to the left side or right side or upward or downward. So then similarly for the other end also you do the same thing and join this. So you'll get the diagram, this which is fixed bending moment diagram, and the earlier which is drawn is free bending moment diagram. Clear? So this is the final bending moment diagram. So this ends the problem of the frame, which is solved by this is a non-sway problem, which is solved by matrix stiffness method using system approach. Thank you.